Hi and welcome, ladies and gentlemen. Today we are talking about shortest path in graphs, and that is the Dijkstra algorithm in this case. Well, what we want to do is we want to find the shortest path between two vertices. And there the Dijkstra algorithm comes in, and that is greedy optima. Well, if you don't really, if you're not familiar with graphs, have a look at graphs. I blend in a video that is really good about it. It's one of my own, so have a look. Well, we have certain preconditions for the Dijkstra algorithm to work. And one of them is that we have no negative edges in our graph. And the other one is that we don't have any cycles in our graph. Otherwise, we have to do a cycle detection before we run the Dijkstra algorithm and have to remove all the cycles in it. Well, let's have an example to make it clear how the algorithm works. Well, at first, we have this graph on the left, and we have the nodes 1, 2, 3, 4, 5, and 6, and we want to find the shortest path from 1 to the node 6 in this case. So for the Dijkstra algorithm, we basically have three lists that we maintain. At first, we want the minimum value to reach a node. Then we want the predecessor that gave us this minimum value. With that, we can figure out the path we want to get in the end. And then we need a queue, and the queue is a sorted list, but sorted by the minimum value. And that stores which node has to be worked on next. Alright, so let's have a look at this example here. We initialize this list with the minimum value infinity for all the nodes apart from the first node, and that is the node 1 here. And our predecessor will always be none. And our queue will have at first our start node, the 1 in it. Alright, so let's have a look here. So now we are looking for each next node, or each child node, however you want to call it, of our current node, and that is the 1. So here we have a look in our table, and we see that the minimum value from 1 to 1.5 to 2 is 1.5, and that is smaller than our infinity, so we can put it in as our minimum value. And then we put in our predecessor, that is 1, and we also append our node 2 to our queue. And also we remove the 1 from our queue because we are currently working on it. Then the next child is actually the 3. So the minimum value from 1 to 3 is 1, and it is smaller than infinity before, so we can put it in our table. And we write down our predecessor, and that is again 1. And then we see in our queue, we have that sorted by our minimum value already. So the 3 is the node we work next on in our algorithm. But at first we have to finish all children of the node 1, and there is the next node 4 still left. So in our next step, we have our value as infinity of node 4, our minimum value, and 2.7 is smaller, so we put it in, and then the predecessor is 1 again. And 2.7 is also the biggest minimum value of all the nodes, so it comes last in our queue. Alright, so let's work on node 3. Node 3 has just one single successor, and that is the 4. And now we sum up the 1 that we have as minimum value to the node 3 plus the costs from node 3 to node 4, and that is 3.5. So we are at 4.5 overall to reach node 4. But the minimum value of node 4 is 2.7, and that is smaller. So we don't change our minimum value in our table there, and we also don't change the predecessor. Alright, so now we worked on node 3 and node 4 is already in our queue, so we don't have to append it there. Alright, so the next node we work on is node 2. Node 2 has no children, so we are done with it and we can remove it from our queue. The next node we work on is node 4. Well, node 4 has 2 children, the 5 and the 6, and we go through each child. The next node is 5, and we have a value of 1.1, and the value of the node 4, the minimum value is 2.7, plus the costs from node 4 to node 5 is 1.1, so we have overall costs of 3.8, and these are smaller than infinity, so we write it down in our table here, and we write down as our predecessor the node 1. Alright, so there is another child, and that is 6. Well, 6 is, the costs for node 6 are from 4 to 6 are 1.5, plus the costs from 1 to 4, or the minimum value that we had in our node 4 is 2.7, so we have an overall cost of 4.2. So our list stays what it is, our queue, and we have to work on node 5 now. And node 5 doesn't have any children, so we can remove it from our queue, and we have now node 6 on the first position in our queue, and that means that it is smaller than all other, or the costs are smaller than all other nodes in our list. So since node 6 is our target node, we are finished at that point. Alright, so let's go ahead and implement that in Python. For that, I create a new file here, and I call that Dijkstra.python, and there I want to use the code from another video of mine, and that is where we talk about the adjacent matrix of nodes. I blended it now. If you didn't see it, have a look at it, and that will explain a lot of the code. So I want to copy all of this here, which is basically the graph code plus generating an adjacent matrix. Have a look at the video, there is everything explained in detail. Alright, so let's go in here and create another method called shortest path Dijkstra, and there we give it the self attribute as usual, and we want to have a source node, and we want to have, or let's say source node name, and we want to have a target node name. And we will say computes the shortest path between source node name and target node name. And it will return returns the nodes or the path from source node name to target node name, as well as and we also want to give it the distance, the minimum distance, as well as the minimal distance between them. Alright, so what we do here is we give it the node name, but we want to work with an adjacent matrix, so what we actually need is an index for the source node name, and we store that actually up here in our vertex, which is a helper method or a helper class for our graph. And there we can go in and we also have a list of nodes. So we can say source index is equal to, and there we say x for, oh no, we want x dot, how did I call that here? I think, index, x dot index for x in self dot nodes if x dot name is equal to, and there we need our source node name. Alright, let's copy that and we do the same for our target. And that gives us a list. So we want the first element because we implemented it like that there will be only one element having that index. And we need to rename this to target index. Let's write here compute index for node. Alright, that looks good already. So what we have to do next is to create our values, our initial values, and get our adjacent matrix. So at first I want to have my adjacent matrix. I call that adj matrix, and I use a method that we created in another video, and that is called getAdjacentMatrix. And that will return us the adjacent matrix of the graph. Let's say here generate adjacent matrix. Alright, so good so far. Now we need to store a list of predecessors. Stores, and that will store the predecessor to a node with minimal costs. So stores the predecessor with minimal cost, and there we say simply predecessors, and that will be for now a list consisting of none for each individual node, and there we can use the length of our adjacent matrix, which will give us the nodes, the amount of nodes in our in our graph. Alright, and what else do we need? We need our cost matrix in the end, or the costs for each node, the minimal costs. We have to store those. And here stores the minimal costs for each node. And that will be costs, and that is also going to be a matrix. And there I want to use numpy.inf, or inft it's called here, inft, and again times length, and we want our adjacent matrix here. Alright, so now we have almost everything. We need just one more thing, and that is our queue. I call it queue, you can call it also list or whatever you want. And there we want to start with the first node, and that is our source index. And then I go in and say, while this queue is not empty, while length of the queue is greater than 0, is the same as asking if it is empty, then what I want to do now is I want to check at first, or I want to get my first node from the queue. So I say my current node is equal to the first element in the queue, and then we will work on that, and then we can remove it from our queue. So we can say here our queue is our queue without the first element. Alright, so then we want to go through all the children of our node and we will find an edge in our adjacent matrix if the value in our adjacent matrix is greater than 0. We said if it is 0, then the edge doesn't exist. So we go in and say for successor in range, and there I want again our length of the adjacent matrix, because that will give us all the nodes, and then we want to check if the adjacent matrix, and there's the current node, and our successor is greater than 0. Then we want to go in and check if the distance between the value our node has currently in our costs matrix or in our costs list is smaller or is greater than the value from our current node to our successor. So if we write that down, we can say if the costs of successor are greater than, and there I want the adjacent matrix from our current node and our successor plus the value. Let's say pass here for now, because I want to add a little thing to our queue, and that is that we store in our queue also the value. So here we store not only our source index, we also store our source index and 0 for the beginning. Alright, so if the costs are greater, then we can say our down here. If we say our costs are greater than the value of the current node plus the costs from the current node to the successor, then the costs of the successor is equal to, and there we take exactly this statement. And what else do we want to do? We want to change the predecessor of our successor. So predecessor of our successor is equal to our current node. Alright, so good so far. What do we have to do also? We also need to add the nodes or the child nodes to our queue. So we say here queue.append, and there we want to append the successor, and that will be a tuple of our successor and the costs of our successor. Alright, so good so far, and here I have to do the bracket further out. Alright, so good so far. We have now almost everything in here. We add that, so that is good. Now we can also stop if the element at the first position in our queue is already our target node. So if q0 is equal to our target index, then we can say we are done with it, because there will be no node with a distance or with a value smaller than our node as position 1 or position 0 in this case. So we can say here break But before we do that, we also need to sort our queue. So I go in and say queue.sort, and I want to give it the key because we store there our costs. So I want to give it here our key, and that is in this case a lambda function that gets our tuple, the successor and the costs, and I want to return just the costs here. So we just sorted on the costs. Alright, so that should be our while loop. Now we just need to find the path, or find the minimal path. And there we go in and say while our predecessor, of our node, we will define the node in a second, is not equal to none. Then we go in and say at first pass, and let's start here with we need a path list actually, and that will start with our target index. And then we want to go in and say node equals target index, so we know where we can start. And here we need the predecessors list. So what do we do then? Then we say node equals, and we say predecessor node, and we want then also to path dot insert, and there we want to insert it at position 0 because we want to have the list from the beginning to the end and not have to reverse it again. So we put in here the 0 and node, and then we return our path and we return our minimum value, and that is the costs of target index. Alright, so good so far, and let us try it out if that works. So we go in here, we print here a few things. Let me say print here so, and let me make 5 equal signs. Then I say shortest path from 1 to 6, like this. And then I say print g dot shortest path Dijkstra, and that gets our start index and our end index, and that is in this case a, or not index, the name, and we want f. So let's run it and see if everything works as expected. And we get here a list index out of range in line 88. So here we actually want the 0, not the 1 there. Then we have another list index out of range, and that is in the 114. If Q0 equals our target index break, and we also need to check whether if length Q is greater than 0 and this holds. And there we find our shortest path, and that is exactly the same graph, just where we, as in the example, just that we say 1 is A, B is 2, and so on. So, and here we find our shortest path 0, 3, 5, and that is actually true, because we started when we indexed our graph initially in our example with 1, so we had the 1, 4 to 6, and here we have the 0, 3 to 5 because we start indexing at 0. So ladies and gentlemen, if you liked this video, give it a thumbs up. As usually, you find the source code in the description down below in my Git repository. And I would really appreciate if you subscribe to the channel to always get informed whenever I'm uploading new videos. That's it for me. Have a great day. Bye.